Okay, let's walk through how to run this code like I mentioned in the slides to generate these confidence intervals so that you can see kind of what they're doing under the hood. So the first thing I'm going to do is I'm going to load the per package because we're going to be using that since we're doing some iterating like we had done when we're doing the permutation tests or the bootstrap. Okay, so now the next thing I'm going to do is just generate that initial code that I had shown in class. And so as I mentioned, I'm looking at the relationship between wage and age. And here I've got this truth. So in this made-up land that I've invented, wage is equal to 2 times age plus some error term. And so what that means is for a 1 unit increase in age, it yields a 2 times increase in wage. And so if age is equal to 30, then the wage is equal to 60. So in this case, I'm going to say that it's 60,000. So people who are 30 make $60,000. People who are 10 make $20,000, and so on. So obviously this is nonsense in the real world, but this is a made-up land where this is true. So this is the truth. 2 is true, 2 is fixed. This is our beta 1. Our true beta 1 is 2. The beta 0 here is just 0. There's no intercept in this model. So our true beta 1 is 2. And as I mentioned, age is normally distributed in my made-up land with a mean of 30 and a standard deviation of 10. And our error epsilon here is also normally distributed with a mean of 0 and a standard deviation of 10. Okay, so this is the information that we need. And essentially what we're doing here is, in practice, when you are fitting a linear regression model, often you have just one data set, so just one sample from some larger population. And obviously, often this beta 1 value is unknown. That's the thing we're trying to estimate. But I've created this contrived example where that's not the case, so we can actually see kind of the operating characteristics or what it means by what this confidence interval actually means. And so let's generate this data. So essentially what's happening here is we're going to be sampling from this distribution many, many times. And so from this population many times. And so each sample is going to be equal to 100. So we'll have 100 people in each sample. So I'm going to use data frame. So this is going to be like my sample. Age is going to be equal to random normal. So this R norm generates a random normal variable. So this R norm basically samples from a random normal distribution. It samples it n times with a mean of 30 and a standard deviation of 10. Okay, so let's see what that does. Let's just take a peek at what that sample looks like. We've got a data frame with 100 observations, 1 variable age, and this is normally distributed with a mean of 30 and a standard deviation of 10. So if I were to plot this sample, I would expect it to be approximately normally distributed. I would expect the middle to fall somewhere close to 30. And it looks like that's kind of approximately, well, that's approximately true. Okay, so now let's create our wage variable. So sample wage, this is going to be equal to 2 times age. So using our truth here, 2 times age plus our error here, epsilon. So for that, I'm going to generate another random normal variable and generate 100 values here, this time with a mean of 0 and a standard deviation of 10 based on this error that we know is our truth. So again, we don't usually know this true value. We also don't usually know this true value. And so that's why this is a strange situation where basically I'm saying we know the true population and we're sampling from that population many times to sort of get some greater intuition about what's happening in a confidence interval. Oh, and I need to have a $sign here to make sure that works. Okay, so sample $wage. So I'm creating a variable wage in the sample data frame, and that's going to be equal to 2 times age plus this epsilon term. And so let's take a look at what that looks like. I can plot that using Ggplot as well. And so I'm going to plot the sample data, and this time I'm going to plot wage. And we can see what genome histogram looks like. And we would expect this to be also somewhat normally distributed, and we would expect it to have a mean somewhere around 60 because we know it's about 2 times our age variable, and it looks like that's approximately true. Okay, so this is a single sample. So let's say generate, we'll call this generate 1. So now let's calculate a confidence interval for this sample. Oh, and I'm going to go ahead and set a seed just to make sure we get the same thing every time. Okay, so now what are we going to do to calculate a confidence interval? Well, we're going to take the model, and we're going to do LM, this is linear model. We're going to do wage tilde age data equals sample. So that's going to fit our linear model. We've got an intercept close to 1 and a slope of 2. And then we're going to want to take the confidence interval, the comp.int of this model, without a dot, comp.int of this model to get that confidence interval. And if I just want to pull out the bottom piece here, I can do this. I can just take the second row. And so that's going to give us the confidence interval for age, 1.81 to 2.21. So that's our confidence interval for age. And again, this is just in one sample. And we know the truth here. If the truth is fixed, the truth is 2. And even when we don't know the truth, so even in the situation that we're dealing with often, it's still believed to be fixed. And so this is where statistics gets a little bit philosophical. But we believe that that beta coefficient is true and fixed somewhere. It's not random. And so what that means is that if we were trying to assess the probability that that beta 1, the true parameter, falls between 1.8 and 2.2, well, that probability is either going to be 1 or 0, because it either is or it isn't, because we're talking about a fixed value. And since we know it's 2, the probability that 2 is between 1.8 and 2.2, well, of course that's 1. It's always between those values. So that's not really a meaningful measure, and it's not what a 95% confidence interval is getting at. The 95% confidence interval is getting at the whole sampling procedure, which is why we want to simulate that to be able to sort of emulate what's happening here. Okay, so to make this simulation, I'm going to go ahead and create a function. And I'm just going to copy the code that we've created here into my function. So I'm going to call this get confidence interval or get CI. In this function, I'm going to have one argument. I'm going to have an ID argument so that I can basically, each time I get a different sample, I'll just have a different ID for it. Okay, so let's copy this code here. So this code is generating my sample. It's generating my age variable, and then it's generating my wage variable. And then let's copy our model code here. And so then it fits a model, and then we create this confidence interval. And I'm gonna actually, I'm gonna clean this up a little bit. I'm gonna have the output be a data frame. So I'm gonna say, I would like to return a data frame where I'm gonna have a variable called lower bound. That's gonna be equal to the first value here. So if I run this here, that's gonna be the lower bound. And then upper bound is gonna be equal, to the upper bound, and then I'm going to add a variable for ID so that I can track what the ID is that we're passing. And then we need to have one more parentheses to close our return statement. So what we're doing here is we're returning a data frame. And the data frame has 3 columns, lower bound, upper bound, and ID. Let's just run this function one time to see what happens. So if I run down here in my console, get CI, and I set the ID to 1, I end up with a lower bound of 1.88, an upper bound of 2.27, and an ID of 1. If I set my ID to 2, even if I leave my ID the same, but I run this many times, I'm going to get a different lower bound and upper bound because every time this different random process is happening. The only reason I'm setting this ID here is because it's going to make it easier to plot down the road. Okay, so instead of just like doing this where I'm running it 100 times in the console, let's do this programmatically using that mapdf function that we had learned about before. So I'm going to do this 100 times. And so basically it's passing this 1 to 100 to the ID parameter here. And so it's going to look at IDs 1 to 100. I'm going to call this CI. And then before I do this, of course, I want to set a seed so that I can make sure I get consistent results. So let's run this. Let's see what we get. All right, so we get 100 confidence intervals. And we've got a lower bound, an upper bound, and an ID for each of these. And we've got 100 of them. Let's take a peek and see where we miss 2. So the first one that doesn't contain the truth, it's right here, sample 16. So sample 16 has a lower bound of 2.03 and an upper bound of 2.4. And so that does not contain 2. So that's the first one that misses the truth. And it's possible that the only sample that we saw could be sample 16 because it's just sort of a luck of the draw what you end up getting from your sample, when you're doing your sampling. And so if we saw this and we said something like 95, the true value falls between 2.03 and 2.4 95% of the time, that would be a false statement because the true value is 2. It never falls between 2.03 and 2.4. And so again, I'm just trying to sort of help build this intuition about what a confidence interval actually means. Okay, so let's plot this like I did in the slides. So I'm going to plot the CI data. I'm going to leave X out here. I'm just going to set Y. So on my Y-axis, I'm going to have the ID because I'd like to have a different line for every one of my confidence intervals. And then I'm going to use geom line range. And here my mapping, so this line range is going to create a line from an X value to another X value. And so that's going to be my confidence interval. And so my minimum X value I want to be that lower bound. And the maximum X value I want to be the upper bound. Let's just see what that does. Okay, so there are my 100 confidence intervals. To help us sort of ground and get a little bit of a better sense of which ones contain 2 or are truth, I'm going to add a vertical line. So this geom B line adds a vertical line. And so I can set the x-intercept for this vertical line. I'm going to set that to 2 because that's my truth. I'm going to use LTY as the line type. And if you set it equal to 2, it makes a dashed line. So now I've got this nice dashed line at 2 to sort of give us a sense of, okay, which ones are or are not crossing over that line. And then one last thing to just make it a little bit easier visually to sort of get a sense of this. So I'm actually going to set a color. And so I can do color equals. And what I'm going to do here is I'm going to set an indicator. And so if the lower bound is greater than 2 or the upper bound is less than 2, then I'm going to have it have a different color. So let's see what that does. Okay, so that pops out these 1, 2, 3, 4, 5 that don't actually contain 2 in their interval. So I just set this lower bound greater than 2 or upper bound less than 2. I have this logical argument in the color statement. And let's just fancy this up a little bit more. I'm going to color these. I'm going to use the scale color manual to manually color these. I don't really like the red and the blue. I think it'd be better to just color these maybe black and red. And so I want all of the ones that are that contain 2. So the good ones I want to just be black. They don't really need to stand out. The ones that miss I want to be red so they stand out a little bit more. There we go. So that looks good. And then I'm going to get rid of this legend over here because we don't really need that. So I'm going to use the theme. function, and I'm going to do legend position equals none to get rid of that. Okay, so let's walk through quickly what I did with this plot one more time, and then we'll talk about what the results are. So I'm using this CI data frame, which, as a reminder, is that data frame of the confidence intervals that we generated. We generated 100 of them from our true population. And on the y-axis, I'm plotting the ID, and so I just created this ID variable in these confidence intervals so that we could sort of separate them out easily to plot them. And then we're coloring these lines based on this logical statement. If our confidence interval does not contain 2, so if the lower bound is greater than 2 or the upper bound is less than 2, then it's going to have a different color, in this case red. Then this geom line range, I'm setting the minimum value to the lower bound and the maximum value to the upper bound so that I get these nice lines. To ground this, I'm using a geom V line and setting the x-intercept to 2, and this LTY equals 2 is what makes it a dashed line. And that's just so that we can sort of see where our true value is. And then I'm fancying it up a little bit. I'm changing the colors to black and red, and I'm removing the legend. So looking at this plot, what this shows us is, if we were to repeat this sampling procedure many, many times, 95% of those that we completed, so these 95 black lines, they all contain the truth. They all contain our true value too. And that's great because that means that our linear regression model and our confidence intervals work like we think they do. And 5% of the time, these 5 red values, those ones missed. Those ones don't contain the true value. And so what's important to point out here is that when you're doing a regression model on your data, you're just seeing one of these lines. And so you're just reporting one of these lower bounds and one of these upper bounds. And so it's incorrect to make any kind of probabilistic statement about the true beta coefficient with respect to that lower bound and upper bound in particular. Because the true beta coefficient, even though you don't know it, is fixed. In this case, we do know it because I said it. But in reality, you don't know what it is. But just because you don't know what it is doesn't mean it's not fixed. It's still a fixed value. And so it either is or it isn't within that confidence interval. There's no probability associated there. The place where the probability comes in is when you talk about the entire sampling procedure. So if we were to do this process many, many times and calculate many different intervals, but all using the same procedure, we would expect that this procedure will yield confidence intervals that contain the truth 95% of the time. So 95% of these confidence intervals, with an S, contain the truth, but that doesn't mean that the single confidence interval contains the truth with any kind of probability. Does that make sense? Okay, so what I want you to do is I want you to recreate this plot that I've just created, and I want you to do this a couple times to sort of gain some intuition about what confidence intervals mean, and then I want you to write up a short description of what we've done and what the definition of a confidence interval is in the context of a specific confidence interval as well as in the broad context. So I'm going to just walk one more time through this code just to make sure that it's all clear what we're doing. And so I've created this function called get_ci. Oh, and importantly, at the very top, I loaded the per package. That's an important piece because we use that for that map_df. Okay, so I have this function, get_ci. It has one argument ID. And the first part of this function is just creating my sample. So I take a data frame and I randomly pull n, which in this case is 100, samples with a mean of 30 and a standard deviation of 10 to generate my age variable. And then I calculate wage in this sample by taking 2, our known truth, our known true beta, times the age variable that I just created, plus our epsilon, which we have the truth for because this is, in this case, I know that the true values because this is part of Lucy land. And so now we've created our age and our wage variables. And then we fit a linear model on this sample. So we fit a linear model predicting wage from age using this sample. And then we pull out the confidence interval of this model. So this code here will pull out the lower bound of this model for age. This code here pulls out the upper bound of this model. And then I also include the ID in my data frame. And that's because it makes it easier to plot. So that's what this get_ci function does. I set my seed to 7 and I run this function 100 times. You can try running it 10 times. You can try running it 1,000 times to sort of see if you get different results. But you want to run this several times and then take a peek at that data to see what it looks like. You should have 3 columns, lower bound, upper bound, and ID. And then let's create a plot. And so we create this Ggplot that basically shows these confidence intervals and colors the ones that miss, so you can estimate how often you miss. If you set your seed to something different, which I encourage you to do, you might get a slightly different answer than I do. Hopefully you'll get something close to 95%, but because there's random process involved here, sometimes you might get something a little bit higher or a little bit lower. And it especially depends on how many samples you look at. Okay, so I want you to try that yourself, and then I want you to describe what you did, and so that you can sort of describe a little bit more clearly what a confidence interval actually means.